Okay, so as promised, here is the video lesson for chapter 6.1, which is the first lesson on confidence intervals. We're going to start off with just a little review on something we did in chapter 5. So part A says find the z-score for which 90% of the distribution's area lies between negative z and z. So when we have this type of problem, if we think about our bell curve, I want to know which two values does 90% of my data fall between. Okay, so I've done this a couple of different ways. The way that I like to do it is using the graphing calculator. So we need to do inverse normal because we're finding a z-score. So inverse normal, but then we need to figure out what area we're going to plug into inverse normal. So if this middle area here is 90%, that means the two outside areas, so I'm going to say the areas in yellow, need to add up to 10%. Now they get evenly split, so that means this first part is 5%, and the back is 5%. So if I'm going to find this z-score here, which is going to be negative, I'm using the area of 5%. So in my calculator, we can go to the inverse normal function, which, just to remind you, you go to the vars button, second vars, and number 3 is inverse normal. And you're going to put in that 5%, which is 0.05, comma 0, comma 1. You just click enter, and we get negative 1.645. So that means my z-scores are positive and negative 1.645. Okay, so now we're going to do the same thing for part B. Find the z-score for which 95% of the distribution's area lies between negative z and z. So the area, now if you notice up here, this was 90%. The area that we used here was 100 minus 90 divided by 2. So the area that we're going to use in this one is going to be 100 minus 95 divided by 2, which gives me, what is that, 2.25%. So I'm going to do inverse normal, 0.0225, comma 0, comma 1. And that gives me z-scores, when we plug it in the calculator, of positive and negative 1.96. And then last but not least, we have 99%. So this is going to be 0.005. Oh, sorry, hold on. It's going to be half of 1%. So half a percent, which is 0.005. So then again, when we do our inverse normal on the calculator, 0.005, comma 0, comma 1, our two z-scores are plus and minus 2.576. Okay, so why did we choose these numbers? So these three numbers, 90%, 95%, and 99%, are going to be used a lot throughout the rest of the chapter for confidence intervals. Okay? All right, so now let's get moving on the notes here. So inferential statistics, we use the sample statistics to estimate the value of an unknown population parameter. So we'll be given a sample of data, okay? If our population was all grocery store workers in a given county, we'll probably be given a sample of 100 of the total number of workers. So it's not realistic to work with populations because there's so many people. So, and when we say we're using the sample statistics, that would be information like the mean, the standard deviation, and so on and so forth. Okay. Now, the first thing we need to do is it starts with finding a point estimate. So the point estimate for a population mu is a single value estimate, for a population parameter. So essentially, we're going to estimate either the mean or the standard deviation of an entire population just by using what we know about a specific sample. Okay, so let's take a look at example 1, finding the point estimate for population mu. So we've got all of this data. An economics researcher is collecting data about grocery store employees. Okay, so that's where I came up with that. The data listed below represents a random sample of number of hours worked. So I'm going to highlight that because that's important. So it's the number of hours worked. Okay, number of hours worked. And I guess that's probably per week. And then our sample size is 40 employees from several grocery stores in the county. Find a point estimate of the population mean. And this is not an M. I don't know why it printed out like that, but it should be a mu, okay, because that represents the mean for the population. So essentially what we're going to do here is we're going to calculate the mean for the sample, okay? So my sample mean is just the average of all these numbers, okay? So we're going to add, and I'm using just fancy letters here like we always do, but it means add up all of the X values and divide by the number of entries. There's 40 employees that responded to the survey. And if you add all of these numbers up, I'm going to give you the answer here. We would get 1,184. So the mean number of hours worked by this group of employees was 29.6 hours. Okay, so the point estimate for number of hours worked per week by grocery store employees in the county is 29.6 hours. Okay, so essentially what we did is we're generalizing pretty much here. What we're doing is we're generalizing because we are taking just a small sample. I mean, if we counted all of the grocery store employees in the entire county of Monmouth County, I don't even know how many there would be. I'd say there's probably well over 2,000, right? So what we're doing here is we're only taking 40 of those people, but we're saying, hey, since these 40 people average 29.6 hours per week, we're going to be we're going to generalize it, and we're going to say for all of the grocery store employees in Monmouth County, they average about 29.6 hours per week. Now, this isn't great. Okay, this isn't great. It's not, we always say it's not good to generalize, not good to stereotype. It's kind of along the same lines. So we have something called a sampling error because the probability that the population mean is equal to the point estimate of the sample is very highly unlikely. Okay, so basically it's unlikely that X bar is equal to mu. Okay, so it's very unlikely that the mean from our just sample is equal to the mean of the population. So we have something called the sampling error, which is the difference between the point estimate and the actual population parameter value, okay? And it's really simple, but you have to know what the actual population parameter value is. So for mu, if we knew what mu was, the sampling error is the difference of X bar minus mu, okay? Mu is generally unknown, and it varies from, and X bar varies from sample to sample. I don't know where that went, but that's supposed to be in there, okay? All right, so sampling error. If the actual value for mean hours worked for the population of grocery store employees in a given county is, I don't know, some of this stuff didn't print out, so I don't know if you have it on your notes, but this is supposed to say, if the actual value for the mean hours worked for population of grocery store employees in a given county is, it should say mu equals 32.4. That should be in the problem. Calculate the sampling error for the data collection in example 1. So again, we're just going to do X bar minus mu. Okay, so our X bar from sample 1 was 29.6. We're going to subtract the population mean, which is 32.4, and we get a sampling error of negative 2.8. So that means our estimate was 2.8 hours less than the actual average. So our point estimate is 2.8 hours lower than the population mean. Okay. All right. So there's always going to be error. There's a margin of error. I'm sure when you have done science labs in the past, you've learned how to calculate the margin of error. There's always going to be some kind of, or the possibility, I should say, of some kind of error with human data, okay? Human entries, human samples, whatever it may be. So an interval estimate creates an interval for the population mean, okay? So it creates estimates for the population mean, but it's in an interval form. So instead of saying, you know, a good estimate would be this specific number, we're going to say that a good estimate would be that our mean falls between this number and this number. And on our next page, you'll be able to see a diagram of what that kind of looks like. Okay, let me just zoom in here. So here is a diagram, and this is called an interval estimate. Okay, when we get to creating confidence intervals, this is exactly what a confidence interval looks like. So you've probably been seeing confidence intervals a lot without really knowing what they are. So this is what a confidence interval is going to look like. So basically, instead of saying, so we have our point estimate here of 130.8. So that means we had some kind of sample, and the estimate for the mean of the sample was 130.8. Okay, now it's not very likely that that is going to represent an entire population. So we can create an interval estimate, and we can say, all right, well, if I can figure out my margin of error, then I know that my range falls somewhere between 115.1 and 146.5. So an interval estimate basically states that the population mean likely falls between 115.1 and 146.5. So it's just giving us a range of possibilities so that you're more likely to figure out approximately what the mean is rather than just pinpointing one specific value, which is very likely to be incorrect. So how confident do we want to be that the interval estimate contains the population mean mu? So the level of confidence is this C value, which you probably have been seeing a lot again in 6.2, but you weren't really sure what it meant. And it really just is the probability that the interval estimate contains the population parameter. So how confident are we? How likely is it that our actual mean for the entire population falls between these two numbers? And then kind of going back to our warm-up problem that we did, the C value is the area under the standard normal curve between the critical values. Okay, so that would be that shaded area. Now, the critical values are values that separate the sample statistics that are probable from those that are not. So they're basically z-scores. Okay, it'd be this negative ZC and positive ZC. And they are values that separate sample stats, so something like the sample mean, that are probable from those that are not. Okay, because sometimes there are numbers that are actually realistic, and it's actually likely that, hey, the mean for the population falls somewhere between these two numbers. But then there's numbers that it's not realistic. So if we said that, the population mean number of hours worked, we'll go back to that grocery store problem, fell between 29 and 30 hours. That's not realistic. That's very unlikely that that's going to be the case because that margin is too small, okay? That interval is too small. So we talk a lot about confidence levels, and we use these confidence levels to come up with our confidence intervals. And if the confidence level is 90%, that means that we are 90% confident that the interval contains the population mean mu. Okay, so in this diagram, C equals 0.90, which is the shaded area, because that's how confident we are. The area outside the shaded region would be these two yellow pieces, and that is 1 minus C, which would be 0.10. The area in just what we call one of the tails would be, let's say if we just looked at this area here, it would be 1/2 of the total area outside, so this is 0.05. And then our critical values for the left and right tails, if we wanted to figure out what the critical value was for this left tail, that means that this value is 0.05. So we can go back to that warm-up problem and we can say, okay, well, hey, for an inverse normal of 0.05, okay, we get a z-scores of plus or minus 1.645. Okay, now the nice thing about this is that there are common confidence levels. So most of the confidence levels that you see, not every single one, but most of them are going to be 90%, 95%, or 99%. Okay, and the critical values that go along with that are 1.645, 1.96, and 2.575, right? When we actually use these critical values in calculations, we only refer to the positive ones. So that's why I only wrote the positive ones there. All right, let's move on to the margin of error, which is probably something that you've heard before, but you might not have seen this formula. So the margin of error is the greatest possible distance between the point estimate, which is just our sample mean, and the value of the parameter being estimated for a given confidence level. So basically the value of the population mean for a given confidence level, okay? So we do have a formula here. It's denoted by E, and E is equal to our critical value times our population standard deviation all over the square root of the sample size. So remember, this is population standard deviation. So that's something that we would need to know from the problem. We need to know the population standard deviation, and then this is our sample size. And this is our critical value for our confidence level. Okay, a couple of other things you need to note is that the sample must be random. And also, n has to be greater than or equal to 30, or data is normally distributed. So if our sample size is bigger than 30, it's fine. You don't have to worry about the data being normally distributed. But if our sample size is only 10, then somewhere in the problem, they have to tell you that the data is normally distributed. So let's find our margin of error. Use the data about the grocery store employees and a 95%, I'm going to highlight that, 95% confidence level to find the margin of error for the mean number of hours worked by grocery store employees. Assume the population standard deviation is 7.9 hours. And then it gives you a little sidebar here. Recall that the mean of the sample was 29.6. So we're just going to go through and we're going to write down all of the variables that we have. So we have our 95% confidence level. C is 0.95. But remember, I still need to figure out what my critical value is. So we could go back up to that chart that we have up here. My critical value for 95% is 1.96. So our ZC is 1.96. What else? Our population standard deviation is 7.9. And our mean of the sample was 29.6. What else? Our sample size is 40. We have that from the earlier problem. And then our sample is, so then we'll just put a little star here. N is greater than or equal to 30, so that's fine. And our sample is random, okay? So now all we have to do is we use our little formula for E, which is above us. And we're just going to plug all that stuff in. So we get E equals Z sub C, which is 1.96, times our standard deviation for the population divided by the square root of our sample size. And we end up getting about, when you plug that in, 2.4. So the wording with these problems is very important. I need you to word them in a specific way. So the way that we would sum up our solution here is we would say you are 95% confident that the margin of error, I'm just going to put MOE, for the population mean is 2.4 hours. Okay, so what does that actually mean? What does that mean? So that means that we're 95% confident that the population mean is either somewhere between 2.4 hours less than our sample mean or 2.4 hours more than our sample mean. All right, we're going to try a couple of these problems down here. We're going to do 13 and 15. 13's pretty straightforward because we have that our confidence level is 0.95, which means our critical value for 0.95 is 1.96. Because again, that's a common one. You need to remember these common ones. You need to write them down. They'll be used pretty often. Okay, so for number 13, we just have to set up our equation. So it's Z of C, our critical value, 1.96, times our population standard deviation divided by square root of the sample size. And we get about 1.86, okay? Now, number 15 is a little bit different because we have a number for our confidence level that it's not a common one. It's not in our list of common confidence levels. So our confidence level is 0.80, okay? So remember what we were doing? We were doing inverse normal, and then the area was just one of the tails. So we need to do 1/2 of 1 minus 0.80. This gives me 1/2 of 0.2, which is 0.10. So if we wanted to find the z-score that goes along with 80%, we would have inverse normal, 0.10, 0, 1. Again, we can just put that in the calculator, and we get a critical value of 1.28. Now, again, your calculator is going to give you negative 1.28, but when we're plugging all of this stuff in for the margin of error, we're going to use the positive z-score. So make sure you use the positive z-score. So now we can just go back and we can plug that all in. We have z of c is 1.28. So I have 1.28 times 1.3, which is my population standard deviation, divided by the square root of my sample size. And we get about, should be 0.19 for the margin of error. Okay? All right, so that was day 1 of section 6.1. I know this sounds like a lot, but you know how we usually do it. I usually break up the sections into 2 days. So now we're going to go into constructing the confidence intervals, which was day 2. So if you need to take a break, I strongly suggest you take a break and then come back and watch the second part of this video. All right, moving along. Confidence intervals for the population mean. So we're still using all of the stuff that we did in the first video, okay? But now we're actually going to construct a confidence interval. We're going to interpret it. So I don't know why my chart didn't pop up, but you should have that chart on your notes. It's the guidelines for constructing a confidence interval. So first, we have to verify that we know the population standard deviation. We have to verify that the sample is random and that either the population is normally distributed or our sample size is greater than or equal to 30. Next, we find the sample statistics, the number in the sample, which we need to know, and we need to find the sample mean. All right, so let me just write these down real quick. After we have our sample size and our sample mean, we then find the critical value, which if it's one of those nice ones, either 90%, 95%, or 99% confidence level, you could just use your chart. If it's not, there's a table that you could use, but I think the easiest way is to just do it on your graphing calculator, in which you could do the inverse normal function of the area, comma 0, comma 1. And remember that area is going to be 1 minus our confidence area. So let's say it was 95%. It would be 1 minus 0.95, and then we're going to divide that number by 2. Most of the time, especially once you get to 6.2, you'll have either 90, 95, or 99. So you could just use your chart to get the critical value. Next step, we find the margin of error using the formula we just came up with. And then finally, we find the left and the right endpoints. So in order to find the left and the right endpoints, we take our mean and subtract our margin of error. To find the right endpoint, we take our mean and we add the margin of error. And then our interval are those two numbers. And so you're also always going to graph your interval on a number line. Okay, you put your point estimate, which would be X bar, and then that gets a dot on it. And then wherever your left endpoint is, you put a parenthesis on. So this would be my left endpoint. And then we would have our right endpoint as well. Right endpoint. And then you shade and darken over the confidence interval. And this would be what a final product would look like. And then I'm going to show you how you can interpret it and change it into writing. Okay. All right. So let's go over to the next problem, which is an example. There's my chart. I guess I wasted time writing on it. Oh, well. Okay. So here's our example, constructing a confidence interval. Construct a 95% confidence interval for the mean number of hours worked by grocery store employees. And I guess we're just using that same example. So remember that this should say X bar is 29.6 and that our margin error is 2.4. So usually you have to calculate these things, but we're still working with the example that we've been working with from the jump. So we're just going to pretend we already did all that work already. So to get your left endpoint, it's X bar minus E, which is 29.6 minus 2.4, which is 27.2. To get the right, it's X bar plus E, which gives me 32. And then we're going to graph this. Sorry, had to make it a little bit smaller. Okay, so now let's graph it on our number line. So I'm going to put my number line. Let's see. Our left endpoint is 27 and our right is 32. So I'm going to put numbers 26 to 33. 26, 27, 28, 29, 30, 31, 32, 33. Okay. So remember, first thing you have to put down is your point estimate, which is X bar. So we need to put a point at 29.6, which is going to be somewhere around here. I put my left parenthesis at 27.2, and then I put my right parenthesis on 32. And then I highlight all that stuff in the middle, or I just darken it. Okay, I also like to write it down in interval notation. So 27.2 less than mu less than 32. Now, the interpretation part is the important part. I want you to format your interpretation the same way every single time. So we always start off with X confidence. So in this case, it's 95%. So with 95% confidence, we can say that and then you always want to put what you're working with. So mean number of hours worked by grocery store employees. Mean number of hours worked by grocery store employees in a certain county falls between 27.2 and 32 hours per week. Okay, and that's how you're going to format your interpretation every single time. All right, let's do one more example, and that will be it. Oh, there's a couple more things after we do this example. So we'll do one more example, and then I'll skip to the notes on the back. Okay, so let's see what we're working with here. So we've got a college admissions director wishes to estimate the mean age of all students currently enrolled in a random sample, so the sample's random, that's good, of 20 students. Now, since the sample size is less than 30, we need to make sure that it's normally distributed. And it does. It says down here that it's normally distributed, so we're good to go. Okay. So again, we have a random sample of 20 students. The mean age is found to be 22.9. From past studies, the standard deviation is known to be 1.5. And the population is normally distributed. Construct a 95% confidence interval. Okay, so let's write down the information that we have. We have our standard deviation is 1.5. Our sample size is 20. Our sample mean is 22.9. And our critical value, well, our confidence level is 90%. So then if we look back at the chart, you would see that the critical value for 90% is 1.645. So before we can actually construct anything, we have to calculate our E. So we have E is equal to our critical value multiplied by our standard deviation over the square root of the sample size. And we get about 0.6. So that means our left endpoint is going to be our mean, which is 22.9 minus 0.6, which is 22.3. Our right endpoint is going to be 22.9 plus 0.6, which gives us 23.5. So our confidence interval and I'll do this in blue, is going to be 22.3 is less than the mean, but the mean is less than 23.5. And then we construct our interval for that. Let's see, we've got some small numbers we're working with here. So let's do 22, 22 and a half, 23, 23 and a half, 24. So 22, 23, 24, 22.5, 23.5. So our point estimate gets literally a point. X bar is 22.9. So we're going to put a big point right there. Our left endpoint is 22.3. So that would fall somewhere in this general area. And then we have 23.5. And then we're just going to darken that up. So again, if you were going to write your interpretation, we have to be very specific about the interpretation. We would say with 90% confidence, we can say that the mean age of college students enrolled at a certain university falls between 22.3 and 23.5 years. Okay? Okay. We're going to skip the next example because I want to get the ball rolling here. The next part just kind of talks about interpreting your results. As long as you format your answer the way that I want you to, you will be fine. So moving on to sample size. Okay, so this is just going to be another equation here. So we would need to determine a minimum possible sample size to have a realistic estimate. So basically what this is going to do here, so given a confidence level and a margin of error, so given a confidence level C and margin of error E, the minimum sample size needed to estimate the population mean is given by, and I'm going to write this down over here, n equals critical score or critical value times standard deviation divided by margin of error, and then we're going to square the whole thing. Okay, so again, it's just another formula. If they ask you to determine the minimum sample size, this is what you're going to do. If our population standard deviation is unknown, you can estimate it using S of x, which is the sample standard deviation, provided that we have a preliminary sample with at least 30 members. Okay? With at least 30 members. So the economics researcher in example 1 wants to estimate the mean number of hours worked by all grocery store employees in the county. How many employees must be included in the sample to be 95% confident that the sample mean is within 1.5 hours of the actual population mean? Okay. All right. So what we have here is we're working with this grocery store problem again. And basically what they're saying is, how many people do we need to have in our sample in order to be sure that this is a good estimate? Okay. So looking back at the information that we have, we were given the population standard deviation. So we don't have to worry about using the sample standard deviation because we were given the population standard deviation. So recalling that our population standard deviation is 7.9 hours. Our confidence level is 90%, so our critical score is 1.96. And then our margin of error. So this is where it can tend to get a little bit confusing. So we want to be 95% confident that the sample mean is within 1.5 hours of the actual population mean. So when you see that phrase and you're trying to find the sample size, that's actually your E value. It's basically saying that our margin of error is either going to be 1.5 hours less than the actual population mean or 1.5 hours more than the actual population mean. And then we're just going to go ahead and we're going to put this in our formula. And we get about 106.56. But you always, with these problems, always round up. Even if the rules of rounding don't tell you to, I can't have a sample size of 106.5 employees. So I have to say about 107 employees. All right, so now in terms of the interpretation, we would write in, let me move this up so I don't accidentally turn this off. In order to be 95% confident that our population mean, our sample mean is within 1.5 hours of our population mean, we would need a minimum of 117 employees in the survey. Okay, now it could be more than 117, but we need at least 117. Oh, 107, not 117. Sorry, I don't know where I got 117 from. So we would need at least 107 employees in the survey. Okay, a lot of information. This is a really long video. I apologize, but it's everything that you could possibly need to know for section 6.1. And hopefully that might clear up a lot of questions with 6.2 as well. If you have any questions, just be sure to reach out and ask me. And yeah, I will chat with you via email if necessary.